So, very good afternoon. Yeah, it's afternoon, right? To everybody present in this auditorium, I am Sayar Basu, currently SD Internet Vistion Corporation. It's a US-based software development company. It basically deals with it is basically a automotive automation company. It's basically a company that deals with digitalizing the cockpit area of a car, especially the cars that deals with automatic gear shifts. So it is basically a an entirely AI based company, and I've been working, I've been selected as a campus placement during my college placements. So, and I've been working with AI for the last 3 years, and for the last 4 to 5 hours in this entire conference, I would say that people are telling that AI will do this, AI will do that, and I can assure AI is doing it. AI is actually it has actually gone a level up with generation capabilities, to be honest. So, and one disadvantage that I have right now is I am almost on the end list of speakers. All of my previous speakers have almost covered 20 to 30% of my slides also. So, I was banning of covering negative and positive food pairing, a small part of computational gastronomy, but we have the maestro here as well. So why cover it from my end as well? So let me start directly with the technology stuff. In the last 4 years, generation capabilities of AI are on the rise. To be honest, for the first time, when probabilistic approach that ma'am has said that there's a predictive analysis going on in fields while producing a crop and as well as while developing food amounts for catering a particular population density or something like that. So when predictive models and analysis comes, we have the concept of rule-based systems. For the very first time in 1990-ish time, in United States of America, there was a particular scientist group, you can say, that developed a if-else-if condition. Like everybody, even if you have a very basic knowledge of computer programming, every programming language has this if-else-if block. It's basically if these conditions suffice, then this set of instructions are executed. If it is not, then the other set of execution are happening. It's at a very clear and this was very rigid, to be honest. It was a very rigid and non-flexible type of if-else-if conditioning that was very much not suitable for predictive analysis of future, which is uncertain. We don't know what is coming up in future with the help of a if-else-if statement. So we gave rise to a probabilistic approach, a predictive approach towards predicting what the next item would be. That is basically the concept of machine learning. Machine learning deals with predicting the next entry to a given huge amount of data. For example, if there are 10 corpus of data and I am to predict the 11th corpus, so I analyze the probabilities of appearance of particular corpus of a data, and we analyze how many times it appears in a particular frequency channel. If it is more than, suppose, a threshold that we technically consider a k-fold cross variation, we consider that if it is a greater than 0.5 or 0.6, and we say that the probability of appearing that same type of data in the 11th corpus is high. So that is the basic concept of machine learning. Then we found out that there are issues with probabilistic approach. Why not use the data itself? Therefore, we shifted towards data-driven technology, that is deep learning technologies, deep learning algorithms, deep learning neural networks. We have convolutional neural networks, artificial neural networks, and as well as recurrent neural networks, which is considered one of the best models that deep learning has produced. So, and finally, the evolution of deep learning to generative AI. I'll quickly show this a hierarchy. This hierarchy is generally considered very naive and a very beginner-friendly hierarchy considered for technologists or like tech enthusiasts. So at the top rests the basic layer of artificial intelligence that deals with Prolog, the language Prolog. It is basically N Queen's puzzle. Whoever knows N Queen's puzzle, it's a basically backtracking concept. It's a very technical thing. I will not go deep into it, but it is very easy to understand. That is an umbrella term for systems mimicking human tasks for the very early period, it started with the rule-based learning systems, followed by machine learning, as I already discussed, that used to learn patterns and in a very probabilistic way. For example, regression, clustering, and also it was basically used for making predictions. That I already said that it was used for predicting the n plus one corpus of a data based on the analysis it used to do with n probabilities of data. And then we had a data-driven shift that was basically dealt in deep learning layers. And finally, we have the ultimate level of evolution of predictive technologies, that is called generative AI, where it generates content, which is technically, to be honest, it is the next word prediction. But we can go one step further and have two types of generative intelligence. So I just already covered this. I'll just do it in a very fast way and stop here. Generative AI and LLMs are the main things of this entire presentation I've made, because Ratatouille Metagen is basically a LLM based, and you can say a RAG. I'll come to it. It's a retrieval augmented generation powered recipe generation machine, that is basically a recipe generation engine, you can say, that is basically used for predicting, rather it is used for generating content of a recipe which is never seen before. It was the basic idea of this entire project was novelty meter. I promised to myself that something which was not seen before is to be generated with the help of generative AI to actually, you can say that, to actually live up to the expectation of the word generation. If you have to generate something, you have to generate the unknown, the unseen ones. You cannot generate the next word you cannot just predict the next future without any base grounding. So there are two types of generative AI, you can say, tech stacks. The one is the encoder-decoder model, and the other is the decoder-only model. So decoder-only model is the one we generally focus on, and decoder-only model is the one we generally develop on. It is a very straightforward model. It's almost similar to sequential models, whereas encoder-decoder model is a very complicated model. It takes a lot of compute part. GPU model, it's a very efficient. The efficiency is quite compromised in encoder-decoder models. If we have FLANT5, one of the examples of encoder-decoder models, FLANT5, and other is BERT-based models, that is regarded as Robert A. So coherent generation using token level probability is one of the features of generative AI. It is based on a token. There's one distinction between a token and a character. A character is not equal to token. In technology, in computer science, characters and tokens are very distinct things. Tokens are somewhat, at times tokens are words, at times tokens are characters, at times tokens are even a sentence. So it is basically semantic based division which is absolutely responsible for this decoder and the transformer to work properly with efficiency. Followed by the capabilities of a generative AI and LLM model. It has a context in it built, like it has a built-in context engine. It understands the context of the sentence before generation of the like it starts, like whenever we use ChatGPT, we understand that it at first understands the concept very much, and then it goes towards generation of the content, understanding what the user asked. And first general purpose agents were also created. So these are very basic things. Now we come to the concept of language models. What are language models? What are its upgradation, and what is the the ultimate layer of language models? The first is language model. Language model is basically the very basic it's the very basic layer of a highest authority of large language models. So it has RNN, as I already said, that it was the deep learning architecture. RNN models were converted with huge amounts of data to form a language model. It was used to analyze natural language from the user while it was conversing, and it was to generate content based on the understanding of the user's input. Followed by that, we incorporated the same language model with a higher corpus of data. For example, if the large language model had 10 to the power 3 rows of data to be incorporated in itself, the SLM has 10 to the power 7 amount of data, and large language model has some billions of data. So massive data compute scaling forms the large language models. So one of the early statistical methods like n-grams predicting next word limited context and shallow understanding was one of the features of language model that I already said that RNN was not that much efficient while it was not very much efficient to understand the concept and context of the input prompt that the user used to give. And followed by SLMs, they were compact. They were absolutely compact, but they were very much inefficient when it came to the generation of very lucid amount of data and and analyzing very high amounts of input variations. And followed by large language models, which is the ultimate level of evolution, you can say, of a language model, which is capable of you can say almost everything that a normal model can do. So when I talk about large language models, we understand that a huge amount of data is incorporated with it, and predicting, basically all models are a derivation of machine learning algorithms. So whatever we do follow the concept of machine learning, that is next level prediction, but next word prediction. So whenever I am predicting the next word, I am bound to analyze the previous part of the entire training data I have. So to analyze the entire corpus of like 10 to the power 7 or 10 to the power 8 rows of data, I need a huge computation power. For that, I need model inference providers. We get it from Hugging Face, we get it from Ollama, we get it from Grok, where there are GPU inference, cloud GPU inference present. They are basically giving us free compute resources so that I can do this analysis part very quickly. So the output is coming in very short amount of time. For example, if I run a model in Ollama in my own local systems, without a GPU, it takes about 7 to 8 minutes for a 2 to 3 billion parameter model, while if I use a GPU, it takes hardly 3 seconds. That's the scaling of a computational inference provider. So as already mentioned. Now comes the phases of an LLM operation. The phases of an LLM operation is basically these are the three things that I've mentioned before 2022. Before 2022, because the LLM operations largely dealt with either build an LLM or fully fine-tune an LLM based on your required necessities, or you can do parameter efficient fine-tuning. Parameter efficient fine-tuning incorporates low-rank adaptation method. It is the LoRa adapters. It's basically the main important thing out of three is basically the parameter efficient fine tuning. Parameter efficient fine tuning is one of the highest efficiency fine tuning you can expect from a smaller amount of data, which is smaller than the training data of the large language model. If a large language model is built on 7 billion parameters and my data on which I want the LLM to perform is less than 7 billion and by a large amount, for example, it is 2 billion, then I must do PEFT so that the model is performing very good on those 2 billion parameters as per my requirement. While if I downscale a model from 7 billion to 2 billion, the overall efficiency of the model is catastrophically destructive. So it tends to forget what it used to know. For example, we have Ganesh Baglar sir, who is a distinguished physicist, once a physicist and now a computer astronomist. If I ask sir a question about physics right now, he will not be able to answer it because he had learned it during his own learning phase, but right now he's fine-tuned himself into a computer astronomist. So he is probably not being able to do the thing. So it's a basic example of building an LLM from scratch, fully fine-tuning and PEFT. The differences. Now comes the concept of prompt engineering, which is very much efficiently used in Ratatouille metagen. Prompt engineering is basically giving the AI a persona to behave something out of entire persona. Like ma'am has already mentioned personification. So personification has been incorporated into an AI with the help of prompt engineering. For example, if I tell an AI to become a chef and create recipes that the world has never seen, it becomes a chef. I'm not sure about the performance efficiency, but it tries to become a chef. So that persona definition is basically done by prompt engineering and prompt tuning. And one of the latest concepts of prompt engineering is chain of thought. Basically, LLM is considered technologically a black box. We don't know how things work inside an LLM, but if we incorporate chain of thought, we do understand how things work, at least analytically. These are the examples. And now comes the concept of retrieval augmented generation, knowledge graph, and graph rack. The newest part is graph rack. But the biggest problem about knowledge graph and graph rag is graph is computationally very slow. Graphs tend to diverge the entire data into nodes and graph nodes, and it analyzes the entire corpus before giving you a particular solution, while as retrieval augmented generation retrieves the data from a given embedded document, which we do by vector embedding, and it gives us the required documents in a very fast lookup time. So I'll just directly show you the example of a one thing I forgot to mention that advantage of structured data over unstructured data. Structured data is the one that we have dealt with in RecipeDB or RecipeDB2 that I've worked with. It's basically the constant schema, the consistent schema that is being there in Ratatouille, that isn't there in RecipeDB. It is very useful for cleaner fine-tuning. Cleaner fine-tuning means the model weights are not garbage. The model weights tend to become garbage after 3 to 4 epochs of training. And it has stable gradient. We don't have a vanishing gradient. And deterministic retrieval means higher RAG retrieval, means the data that is being filtered from the metadata filtering is very high in precision than normal unstructured data. So now the tech part is more or less done. Now it's time for Ratatouille metagen and its comparison with previous early works. So this was the first ever venture of Ratatouille into the research corpus of IIIT-Delhi. It was done by our seniors only, and it was basically a CAR level LSTM model. LSTM model is a long short-term memory model. It's basically an advanced deep learning algorithm that deals with stateful and stateless measures while it generates the content. It was basically data engineered with RecipeDB1. And it was a very good recipe because it was a very good recipe generation engine because it had the backup of a very structured analysis, structured and analyzed database. So I'll not go deeper into the technical stuff because it's not of very usage right now. But one of the key flaws that Ratatouille 1 had to suffer was LSTM overfitting. In technology, overfitting means, in computer science, overfitting means performing well on training data, performing very bad on testing data, that is unseen data. So LSTM overfitting was the biggest problem that Ratatouille 1 had to suffer, and it also had the fully fine-tuned version of GPT-2. As I also discussed, that full fine-tuning leads to catastrophic forgetting. So catastrophic forgetting happened, the model tended to hallucinate a lot, and therefore it was deprecated. Then came Ratatouille V2. Ratatouille V2 was basically an advanced model of Ratatouille V1. It had the parameter efficient fine tuning concept of LLM models like Llama, Mistral, and GPT-2 as well. And it had the QLoRa optimization as well for NF4 quantization. NF4 quantization means the model weights are NF4 quantized so that the garbage values that are incorporating while it is being fine-tuned, it is not that much prevalent. Again, Ratatouille Gen V2 had some issues. The first one is not an issue, I would say, because the first one is the computational hardware problem that I have to suffer as well. And one of the problem that it had was evaluation gap. It could not be evaluated properly because high NLP scores did not actually mean novelty. It meant high coherence with the database only. So what is the point of novelty when it is repeating the data it is present in the database itself? Now, finally, my work, Ratatouille metagen. It is basically a RAG architecture. We have not shifted our focus towards fine-tuning. It is not a fine-tuned model. We have not taken into consideration any kind of GPU trailing and GPU fine-tuning because we believe fine-tuning a model is essentially degrading the model. Because when the database is about 1.18K, there is 118,000 data inputs, and the parameters of Llama that I've used, Meta Llama 8 billion is 8 billion. So degrading a model from 8 billion to 118K is basically degrading the model. So why should I incorporate a catastrophic forgetting mechanism inside a model rather than use RAG architecture? So RAG architecture works like this. If you forget a word, you see up the dictionary. You don't mug up the dictionary all at once. You don't remember the dictionary just to remember the one word. So when a ingredient list is inputted in Ratatouille Metagen, it searches the database. It searches for the nearest entry in the database if it's not exact. If it is there, it analyzes the given constraints and given recipe instructions, and it tends to generate a new recipe which is not exactly similar to the existing ones in the database, but newer and noveler than the existing ones. So in that case, and we have already incorporated, I'll come to the features of Ratatouille Metagel. I've already discussed. The RAG pipeline is basically, this is the main part of this entire presentation. So whenever a ingredient list is inputted, it does a retrieval search. When it searches the retrieval quantity, it does a similarity check. When the similarity, and it also generates the content in a parallel fashion. For example, when it is searching, it is also generating the content. When both are done, it compares both. If the metrics show 0.3 amount of like 30% similarity, then it is more than 30% similarity. It goes and regenerates the newest recipe with a dynamic prompting. Dynamic prompting includes words like become more novel, I've used prompt engineering, for example, in that dynamic novel recipe generation prompting, and I've maintained that novelty all over the generation quality so that it is less than 0.3. The similarity between the given recipe and the existing one should be less than 0.3. Now coming to the choice of LLMs that I have chosen, the choice of LLM has been Llama 3 because you can also see Mistral has a greater parameter ranking than Llama 3, but I have chosen Llama 3 just because Llama 3 was a it was a Goldilocks zone. It fell in the Goldilocks zone, which is basically a balance between both efficiency and computational hardware. So this is the comparison of model evolution, and I've proven with matrices. This is the matrix comparison that Ratatouille Metagen is metrically better compared to Ratatouille 1 and Ratatouille 2. And since LCV people have already tested out Ratatouille 1, I hope that they will like Ratatouille Metagen as well. And this is one of such use cases where I've incorporated Bengali, where I've incorporated Tamil, and I've incorporated North Indian cuisine to mix together and see how the model perform. And I've given, since I did not have any chef in my contact for like the review of the generated recipe, I used ChatGPT to rate the recipe, and it has said that it hasn't, in its entire training data, it hasn't seen any recipe like this ever, and it is 100% humanly plausible. So that is the quality of Ratatouille Metagen recipe that are they generating, and I would like to show the demo and finish the entire presentation. This was the entire UI. So this was the part where I used to enter ingredients. So I'll just give it a simple one: apple, what, rice, anything, the apricot, okay. And give the region Italy. See what it does. This is the recipe that is just given. A harmonious balance of sweet, tart, and earthy flavors, reminiscent of Italy's rich culture, culinary heritage. It has given a set of instructions. The ingredient list is very less, so I believe this is not a feasible recipe. But nothing can be done. If it's a more bigger one, that's perfectly fine. But whatever the instructions I've given, I believe it's good. Have you have to validate it, yeah. So that's the entire, and the computational time it took was 4 seconds. So that's the beauty of GPU enabled.
Is this like
It's a yeah, it's regular, but it's so let's.
there's none of the parent like basically the side के
ठीक है. So let's give a big round of applause. Goodbye.